Welcome back. I am Angelos Treklas, and in today's video we're going to talk about the different modules of OPIL Logistics Automation Library and how to get started with it. As we have seen in other tutorials also, here is the overview of the OPIL Logistic Automation Library structure. In this presentation, we will focus on giving a brief overview of the OPIL modules and a hands-on Getting Started guide. These videos serve as complementary to the main documentation found in RAMP. Most of the modules' documentation are structured in the format of Getting Started, Installation Guide, and User Manual, making it easier for the user to understand and have a hands-on experience with the platform. We will present each module according to its functionality based on this diagram that we have seen before. We start from Robot Agent Node, or RAN.
RAN has two main components: the core, which consists of the task management part responsible for managing sequence of tasks, task updates, load and unload roller conveyors or forklifts, and robot navigation, managing the motion according to the coordinates. The other component is the RAN AGV interface, which is in charge of translating motion to the AGV's native controller. A small overview of different channels: TP to AGV and AGV to TP. Error channel, status channel, description channel. There are specific channels that are directing all the specific actions of RAN. Task management channel that prioritizes tasks, motion channel controlling the AGV's movements, action channel that changes messages between task planner and RAN telling which action to perform, etc. So, how would a task look like? Each task is identified by a number, and it is actually a sequence of motion assignments followed by a sequence of action assignments. For example, here we have task 56, performing 4 motions, maybe like turning, moving forwards, etc., followed by 2 actions that can be lifting, for example. All the assignments are defined by an assignment ID, as seen in the picture. In this diagram, you can see the architecture behind the assignments. You can see here that from the task planner, there is a definition of task 56. Then, it goes to RAN. RAN orders the motion to the robot, and robot gives a status signal back to RAN and TP when the motion is completed. Then, another assignment can be performed following the same method. Now, let's talk about the Sensor Agent Node module.
Sensor Agent Node, or SAN, is actually an Internet of Things module that is responsible for receiving raw data from the sensors and gathering them into a designated entity format containing the necessary information for actions to be performed, providing other OPIL nodes with data. In its plug-and-play format, Raspberry Pi and Revolution Pi modules are also supported. From the virtual components part of OPIL, we have the same modules but incorporated to perform inside the digital twin of the factory. The virtual components RAN, the VC RAN, is a component that mirrors behavior of the actual RAN and enables retrieving RAN messages from OCB to virtual components. For example, looking at the following diagram, you have OCB in the middle managing tasks on RAN and in AGV in the real world, and in parallel, same actions that can be managed through the VC RAN. How are simulations programmed? We install and open the virtual component software and we get the simulation layout file demo factory VCMX that can be found in the documentation. This is a pre-configured layout with an AGV and a RAN router component which ensure the connection between the OPIL library and the AGV. How do we connect virtual RAN with the layout? There is a list of components in the VC software. You can search for Run Router, and on each components panel you select the Connections tab and you define OCB IP, which is the OPIL Automated Platform IP, and the host IP, which is your computer's IP. So OPIL library can communicate with the VC software. Another VC module is the VC SAN. What VC SAN actually does is mimicking the behavior of real sensors. It is easy to use, entities can be created upon the start of the simulation and can be updated at any moment during the simulation. For this module also, another interface, it has been created in VC software. You can gather data from sensors through component interface and translate all component information to JSON format and update the entity in OCB. An entity can be created, updated, or deleted automatically during the simulation. Also here, the appropriate IP addresses have to be set. Details on setting up, it can be found also in the documentation. Another module of VC is the Sensor Actuator Agent Node, VCA-SAN. It is a component that gets real sensor data and incorporates them to VC and the virtual machine. The settings here are similar to SAN. Again, make sure to set up correctly the IP addresses corresponding to the valid ports. Now, let's pass to some core modules that they run in the OPIL Logistic Automation Library server, starting from Sensing and Perception module.
What does this module do? First of all, localization. It makes sure where the AGVs are located. It then defines the topology, meaning that it specifies the nodes and edges of the factory floor plan. When the geometry of the factory is not provided, Sensing and Perception, or SP, can update the geometry in case it encounters differences between reality and the layout model. The Sensing and Perception module, or SP module, is divided in two parts. The local SP provides the position of the AGVs inside the built map of the environment, where the AGV is moving. It also updates the map with new sensor readings or creates maps according to sensor data, Andromeda sensors, and others. Each AGV has its own local SP, which takes care of localization and mapping. The central SP is responsible for creating the topology map of the factory floor plan in order to communicate with the task planner and the human-machine interface. Here we can see another visualization of how OPIL server and AGV are connected with the central and local SP component scheme of communication. Details are further explained in the documentation. Hands-on now. To start the SP, enable the graphic environment by typing xhost local root, and then sudo docker compose up -dsp. You will do this to pull the Docker image of SP. Then, a new display rviz opens and would look like this. In there, you will have all the layout nodes of the factory in blue, and the annotations will be displayed with yellow arrows. As mentioned on the installation guide, these are points of interest where you can find, for example, pick up a pallet, drop a pallet, or perform other actions. Another module that runs on the OPIL server is the Task Planner module. The main goal of the Task Planner is to manage the fleet of the robots. All logistic tasks are optimized based on specifications. The whole task execution is supervised by components of this module. The Task Planner consists of two sub-modules, the Task Supervisor and the Motion Tasks Planning. The Task Supervisor monitors the execution of the task dispatched to the agents. the motion task planning is responsible for the organization of the motion tasks for the robot agents. In order to start working with TP, we have to type the following: sudo docker-compose up-d ts. And as soon as rviz appears, we can see that the system is building the topology of the floor plan. And finally, let's have a few words about HMI, the Human-Machine Interaction Module, the actual interface of the OPIL Logistics Automation Library.
The HMI enables interaction between factory users and OPIL Logistics Automation Library system. It consists of floor plan management, where you can upload floor plan images in PNG or JPG formats, the task management, where task specifications are written in code form in small text snippets on a task specification languages, and other tabs on viewing robot and sensor status in real time. What are the steps on working with HMI? First, you load the layout of the factory. Then, you determine locations of interest, machines, load and unload conditions, for example, type of manipulation between AGV and drop-off resource, type of loads, types of AGVs, expected number of travelers per activity, etc. Afterwards, you can determine different production scenarios according to your factory needs, and in the end, create precise lists of tasks based on these scenarios. We can see here a small overview of the tabs of the HMI. This is, for example, the first tab of the HMI, the overview of the factory floor plan. Then, the next tab will be the floor plan management, where you can define the scale and X and Y offset to determine how AGVs will be moving. The next tab is task management, where all the tasks can be defined in a specific task language. We can see here a small example of how to create a simple task. First, go to Task Manager tab in HMI. Then, copy and paste the task language on the right into the task specification field and click Send Material Flow. The text can be found in the documentation. This specification configures a task to transport materials from WH_1 in the warehouse area to the workstation in the production area. We then create specific buttons in HMI so all these tasks can be run automatically. Then, the User Management tab can be used to specify system settings, IP addresses of AGVs, and new users. Finally, the Sensor Data tab, where signals of any sensor can be viewed. For a more detailed and structured documentation on using the OPIL Logistics Automation Library, you can check on RAMP. Most of the modules there are structured in the following format: Getting Started, Installation Guide, and User Manual. This makes it easier for the user to understand and have a hands-on experience with the library. Also, all OPIL modules can be found there. Some of the L4MS success stories where OPIL has been applied, depending on the factory needs, can be also found in the L4MS pilot section mentioned here. And with this, we conclude the OPIL Logistics Automation Library presentation of modules and the Getting Started guide. Thank you very much for your attention.